that is power semiconductor devices. The next device is Thyristor. Okay. In the first device, I explain about what exactly power diode concept. Then you go for another very important device used in power electronic circuits, that is nothing but a Thyristor. Now we'll see what are the various concepts in Thyristor I want to discuss. That is important for any competitive point of view, either GATE or IS or any PSUs. Okay. First, I want to give some introduction with respect to Thyristor. Later on, I want to explain what are the characteristics and the construction details, all these for Thyristor. Okay. Point to remember, a Thyristor is combination of Thyristor plus transistor. It is a combination of Thyristor plus transistor. It is a combination of Thyristor plus transistor. Okay. A Thyristor is a combination of Thyristor plus transistor. Thyristor and transistor. That is, this total combination is nothing but this is equivalent to Thyristor. This combination of Thyristor plus transistor. Why I am telling that it is a combination of Thyristor plus transistor means the principle of Thyristor is same that of Thyristor and the construction is similar to transistor. That's the reason why it is a combination of Thyristor plus transistor. That means the principle is for this Thyristor. Principle is similar to Thyristor, and the construction is same that of transistor. Why I am telling that this principle is similar to Thyristor means before developing the Thyristor, which device is used for control rectification means Thyristor is used for control rectification. But the problem with the Thyristor is large in size. That's why we are implementing the Thyristor. And in the implementation of Thyristor, the construction is similar to that of transistor. Understood? That's why I am telling that principle is similar to Thyristor and construction is same that of transistor. And also you remember the main motivation of developing the Thyristor is for control rectification. The main motivation of developing the Thyristor is control rectification. Okay. But it is made with, generally it is made with silicon material. You also implement using germanium also, but more preferably silicon. That's why the main motivation of implementing the Thyristor is control rectification, and it is made with silicon material. That's why this Thyristor is also called SCR. This thyristor is also called SCR. That is silicon controlled rectifier. Silicon controlled rectifier is also called SCR. Silicon controlled rectifier. Here we are taken thyristor is one family. In thyristor family, so many devices are there. In that thyristor family, SCR is the first member. But generally, the thyristor family is also called SCR family. Now, here I am discussing the concept of SCR means, that is, we are discussing the concept of thyristor only. Thyristor is also called SCR, that is silicon controlled rectifier. Silicon controlled rectifier. Understood? Then, what is the schematic representation of SCR or thyristor is? What is the schematic representation of SCR or thyristor is? This is the schematic representation of SCR or thyristor. It consists of 4 layers. It consists of 4 layers. That is P1 and N1. This is P2 and N2. And it consists of anode, and it consists of cathode, and it consists of gate. This also consists of gate. This is J1, this is J2, and this is J3, and gate is connected here. This is a schematic representation of SCR. The construction of gate and cathode is given like this also. The schematic representation is also represented like this. This is the actual placement of cathode and gate. Actually, where the cathode and gate arrangement is placed. Cathode and gate arrangements are placed. This is P1, this is N1, and this is P2. This is P2 layer. Okay. Here this is the placement of gate terminal, and here we can place cathode arrangement. This is cathode arrangement. This is cathode, and this is anode arrangement. This is anode. This is gate. This is the placement of actual gate and cathode arrangement, and there is a 3 junctions: J1, J2, J3 junctions. Okay, this is cathode. Okay, this actual arrangement of gate and cathode terminal, and this is the schematic representation of the thyristor. That means it consists of 4 layers. How many junctions? 3 junctions. How many terminals? 3 terminals. But point to remember, always gate is placed, gate is connected to inner P layer. Actually this is N2. Gate is placed connected to inner P layer, and that is nearer to J2 junction. That's why this J2 junction is also called gate junction. This is placed connected to inner P layer and nearer to J2 junction. That's why this J2 junction is also called gate junction. This J2 junction is also called gate junction. Is also called gate junction. Is also called gate junction. That's why a thyristor or SCR is nothing but a 4-layer, 3-junction, 3-terminal. That's why then a thyristor is a 4-layer, 3-junction, S, 3-terminal, 3-junction, 3-terminal. That is 3-terminal in the sense anode, cathode and gate. 3-junction, 3-terminal, S. Bistable. In the sense 2 states, on state and off state. Bistable. Positive feedback. Internally within the SCR, during the operation, a positive feedback action is exist. How it is takes place, later I will give the proof also. But up to now you remember, within the SCR, during turn on, which feedback action is exist? Positive feedback action. A bistable, positive feedback. Semi-controlled device. 4-layer, 3-junction, 3-terminal, bistable, positive feedback, semi-controlled device. Within the SCR, internally, during the operation, a positive feedback action is exist. How it takes place, later I will give the proof also. Then, here I am telling that 4 layers. What is the doping concentration of these layers? What is the doping concentration of these 4 layers? How we can dope these layers? This is P1 and this is N1, this is P2 and this is N2, this J1, this J2, J3. And gate is connected to inner P layer, that is nearer to J2 junction. Then this terminal is anode and this terminal is cathode. Then what is the doping concentration of different layers means? Where N2 is highly doped, thin layer, This is a comparison of different doping concentration. Where P2 is less highly doped, thicker layer, Where N1 is less doped, thickest layer, and where P1 is same that of P2. This is the doping concentration of different layers in the case of SCR. Okay, to operate SCR in different applications, then how we can dope the different layers in the SCR means this is a doping concentration. Where N2 is highly doped thin layer, P2 is less highly doped thick layer, where N1 is less doped thickest layer, where P1 is same that of P2. Then what is the symbolic representation of thyristor or SCR? Tell me. What is the symbolic representation of thyristor or SCR? Okay. Here itself I want to give what is the symbolic representation. What is the symbol used for the thyristor? This is one way to represent thyristor symbol. This is anode, this is cathode, and this terminal is gate. Okay, anode, cathode, gate. Or you also represent symbol like this. This is also thyristor symbol. This is gate, and this is anode, and this is cathode. But point to remember, always in this representation, always gate is supplied with respect to cathode. This anode and this is cathode. This current is IC, gate current. This current is anode current, IA, and this current is cathode current, IK. Okay, then how to write? Where IK equal to IA plus IC, anode current plus gate current. Sum of the anode currents plus gate currents. Cathode current equal to anode current plus gate current. Clear? That's why it is the combination of anode and gate current. Cathode current. Later I will give the proof also. But here this is entering current, this is entering current, this is leaving current. Clearly I will explain. Proof also I will give. That concept I will explain using two transistor analysis of thyristor or SCR. That means always gate is supplied, in general, gate is supplied with respect to cathode. Then these SCRs are called cathode trigger SCRs. In general, gate is supplied with respect to cathode. Gate is supplied with respect to cathode. That's why these are called cathode trigger SCRs. Sir, can you give the gate supply with respect to anode means? Yes, we also implement anode trigger SCRs also. But generally we are using cathode trigger SCR. SCR means we are using the cathode trigger SCR. Sir, can you implement anode trigger SCRs? Anode trigger SCRs means then we can connect the gate supply. If you connect like this also. Gate is supplied with respect to anode also. Then this is called anode trigger SCRs. This is anode and this is cathode, this is gate. Gate is supplied with respect to anode also. But what is the problem with anode trigger SCR means? For triggering of anode trigger SCR, it requires more gate current. But what is the advantage of this anode trigger SCR means? These SCRs are having high dV by dt capability. High D. That means large rate of change of voltages can be withstood by anode trigger SCR. See, sir, why in anode trigger SCRs it requires more gate current? Concept is very simple. This P1, this is N1, this is P2, this is N2. Now this is anode and this is cathode and gate is connected to inner P layer. Okay. This P layer means which is the majority carriers? Positive charge. That is holes are the majority carriers. This is anode terminal means positive terminal. You want to drive this current against positive terminal. This is positive and this is also positive. Now you want to inject the gate current into the P2 layer against positive charge. This positive and positive means repel. If you want to inject the gate current into the P2 layer against positive charge means then it requires more gate voltage in order to inject the current into P2 layer. Because this is positive plate, this is positive plate because of repelling. Then you want to inject the gate current by opposition of that one. We can overcome that opposition, then we can inject the gate current into the P2 layer. That's why it requires more gate voltage. For example, if you trigger the SCR with respect to cathode, means this is positive charge and this is negative plate, then this gate current can easily attracted by the P2 layer. Then within less voltage, we can inject the gate current into the P2 layer now, that is nearer to J2 junction now. Then in this case, it requires less gate voltage. But here it requires more gate voltage with respect to anode trigger SCR. But generally, thyristors means which triggering we are using means cathode trigger SCR. We also implement anode trigger SCR based on our applications. But one advantage of anode trigger is it is having high dV by dt capability. Drawback of anode trigger SCRs means it requires more gate voltage in order to inject the current. Okay, that point you remember. The another point, it may be anode trigger SCR or cathode trigger SCR. Gate SCR is triggered by using positive gate current pulse. SCR cannot be triggered with respect to negative gate current pulse. That means, point to remember, SCR is triggered using positive gate current pulse. It is not a voltage pulse. Using positive gate current pulse only it is triggered. Okay. Then thyristor is turned on or SCR is turned on by using gate terminal, but it cannot be turned off. Hence, it is treated as a semi-control device. I told now what exactly semi-control switch. It can be turned on, but it cannot be turned off by gate terminal. That's why SCR is turn on by gate signal. But it cannot turn off by gate signal. But it cannot turn off. How it can be turned off? Later on we see. Turn off by gate signal. Hence it is a semi-control device. Hence it is a semi-control device. It cannot turn off by gate signal. Hence it is a semi-control device. Understood? This about some introduction to the thyristor. With this, now I want to explain what is the operation of SCR or thyristor. Along with operation, I want to discuss the static VI characteristics of a SCR. Here I am explaining the static VI characteristics means indirectly I am explaining the modes of operation of SCR. The static VI characteristics of SCR is drawn based on the modes of operation. This is very important concept for any competitive point of view. Clear? Okay. This is some introduction to the thyristor. Okay. Now with this knowledge, now we go for the another concept. Yes, is clear? We also give representation like this also. This is also correct. This is anode, this is cathode, this is gate. So represent like this also. Clear? Okay. See the next concept in this. Yes. Now go for very important concept with respect to thyristor. That is static VI characteristics of SCR. Okay. Static VI characteristics of SCR. Static VI characteristics of SCR. I am discussing static VI characteristics means indirectly I am explaining concept of modes of operation. Modes of operation of SCR. Operation of SCR or Thyristor. That means the static VI characteristics of SCR is drawn by using modes of operation. Then SCR is operated in three modes. SCR is operated in three modes. Operated in three modes. SCR is operated in three modes. One is a reverse blocking mode of operation. A reverse blocking mode of operation. A reverse blocking mode. Another one is, that is, for simplicity I am representing like this, RBM. A reverse blocking mode of operation. Next, forward blocking mode of operation. Forward blocking mode. Forward blocking mode of operation, that is FBM. Then forward conduction mode of operation. Forward conduction mode of operation. Forward conduction mode of operation, that is FCM. These are the three modes of operation. SCR is operated in three modes: reverse blocking mode, forward blocking mode, forward conduction. Now, by using these three modes of operation, how we are getting the static VI characteristics, that I want to explain. First, I will draw the total static VI characteristics. Then I will explain how we are getting those characteristics by using these modes of operation. Okay. You draw the static VI characteristics first. Okay. First, you list out these characteristics. This is the practical static VI characteristics. Yes. First, you draw the static VI characteristics of SCR. Yes. This is anode to cathode current. This also anode to cathode current in negative direction. Okay. And this is anode to cathode voltage with negative direction. And this anode to cathode voltage in positive. Okay. Then first I am list out the total characteristics. This is VRB0, reverse breakdown voltage. Okay. This current is called, this small canal, this indicates that a reverse leakage current. A reverse leakage current. This small current is reverse leakage current. And this mode of operation is nothing but a, reverse blocking mode of operation, RBM. A reverse blocking mode. Up to this is reverse blocking mode of operation. This characteristics we are getting without load. Without load. For the same condition, if you connect, then you get the characteristics with load. With load. Okay. Then you draw the characteristics in forward blocking mode and forward conduction. This is the characteristics under forward blocking mode and forward conduction. Okay. This is forward breakdown voltage, VFP0. Okay. This current is IL current, and this current is IH current, holding current. This is which mode? Forward conduction mode. Forward conduction mode. This is forward conduction mode of operation. Okay. This for different values of gate current. We get the characteristics like this. This is for IZ1 current, this is for IZ2 current, and this is for IZ3 current. Yes, where IZ3 is greater than IZ2 is greater than IZ1. In detail about that we'll see, I will explain. Then this mode is nothing but up to this mode is forward blocking mode of operation. This is forward blocking mode. And this current, this small canal, this current, this is forward leakage current. Forward leakage current. Yes, this is forward leakage current. Then this voltage drop is forward voltage drop. Forward voltage drop. Okay. Forward voltage drop. Okay. Then where IL is which current? Latching current. In detail about later on we'll see. Latching current. What is IH here? Holding current. IH is holding current. This is reverse blocking mode. This is forward blocking mode, and this is forward conduction mode. Now we'll see in detail about each mode of operation. This current is reverse leakage current, and this current is reverse forward leakage current, and this is forward breakdown voltage. This is reverse breakdown voltage. Now first I want to start with the reverse blocking mode of operation. We'll see in detail about each mode of operation. That first I am discussing with the reverse blocking mode of operation. Okay. First we want to start with the reverse blocking mode. Reverse blocking mode. What are the observations in reverse blocking mode? All these I want to list out. Reverse blocking mode. You will see in detail about the reverse blocking mode. The name itself it indicates that apply a reverse voltage across the SCR. You want to operate the SCR under reverse blocking mode means apply a reverse voltage across the SCR. If you want to apply the reverse voltage across the SCR means anode to cathode voltage must be negative. Anode to cathode voltage must be negative means you must connect anode terminal is negative, cathode terminal is positive, then only we can get anode to cathode voltage is negative. Yes. Apply the reverse voltage across the SCR. You want to operate in reverse blocking mode na? Then apply the reverse voltage across the SCR. To apply the reverse voltage across the SCR, this is P1, N1, P2, N2. This is P1, this is N1, and this is P2, this is N2. Okay. Now this is anode and this is cathode. Anode is connected to negative terminal. Cathode is connected to positive terminal. Why I am connecting like this? To apply the reverse voltage. and this is gate. Still I am not connecting gate supply. Let Ic equal to 0. Okay. This is J1, this is J2, and this is J3. Okay. Without connecting gate supply, first I want to explain the concept. If the gate supply is connected, what happens? Later on we will see. What is this anode to cathode voltage now? This anode to cathode voltage is negative. That's why thyristor is under reverse blocking mode of operation. Now what is the observation? In reverse blocking mode, what is the different observations? I want to list out here. Every point is important. Tell. Under reverse blocking mode of operation, negative is connected to P1 layer. If the negative is connected to P1 layer means all the majority charge carriers, that is holes in P1 layer, is attracted by negative plate. Is attracted by negative plate means, is it majority carriers cross the junction? No. When the majority carriers are not crossing the junction, then that junction is forward bias or reverse bias? Reverse bias. Because if the majority carriers cannot cross the junction, we don't get anode current, we get only leakage current. That's the reason why this J1 is under which condition? Reverse bias condition. Similarly, positive plate is connected to N2 layer now. If the positive plate is connected to N2 layer, what is the majority carriers in N2 layer? Electrons. Electrons are the majority carriers. All these electrons are attracted by positive plate. That majority carriers will not cross the junction. That's the reason why J3 is under reverse bias condition. Internally, N1 is supplied with negative potential. P2 is supplied with positive potential. Then because of this, the holes in the P2 layer crossing the J2 junction. The electrons in the N1 layer crossing the J2 junction. That means at J2 junction, which carriers cross the junction? Majority carriers cross the junction. That's the reason why J2 is under forward bias condition. That means in reverse blocking mode, J1, J3 is reverse bias and J2 is forward bias. Under reverse blocking mode of operation, which junctions are forward bias and which junctions are reverse bias? J1, J3 is reverse bias and J2 is forward bias. Clear? The generalized statement is also given like this. In reverse blocking mode of operation, outer junctions are, this is a generalized statement, outer junctions are reverse bias and inner junction is forward bias. And inner junction is forward bias. Outer junctions are reverse bias and inner junction is forward bias. Okay, this is one observation. Tell. For clearly understand this concept, I will analyze the thyristor is with respect to switch operation. Okay, I am assuming that each junction acts as a one switch. If you assume that each junction acts as one switch means, if the junction is under reverse bias condition, I will treat it is a open switch. If the junction is under forward bias condition, I will treat it is acts as a closed switch. Okay. Now let us assume that for clear understanding, I taken this equivalent. I am explaining with this equivalent. Let us assume that J1 acts as a one switch. This is J1. And J2 also acts as another switch. This is J2 and this is J3. This is a switch equivalent representation of thyristor. It is under which condition? Reverse blocking mode. Okay. This is J1, this is J2, this is J3. J1 is forward bias or reverse bias? Reverse bias means open switch. J3 is forward bias or reverse bias? Reverse bias means open switch. J2 is forward bias or reverse bias? Forward bias. That means J2 is closed switch. But even though J2 is closed, but still J1 and J3 is open. Hence, under reverse blocking mode, SCR acts as a open switch. Under reverse blocking mode, SCR acts as a open switch and blocks which voltage? Reverse voltage. Therefore, SCR acts as a open switch. SCR acts as a open switch and blocks reverse voltage. This is the second observation. See the third observation based on this reverse blocking mode. Once it acts as open switch, there is no any forward current. But practically, because of stored charges in junction layers, because of minority charge carriers, there exists a small reverse leakage current. Practically, because of open switch, that is, there is no current from anode to cathode. But practically, a small parallel, you note down all these points, okay? Practically, a small reverse leakage current is exist. This is the third observation. I am explaining the concept. We are applying the reverse voltage. Still we are not connecting the gate supply. See in the characteristics. Under a reverse bias condition, means if you apply the negative voltage across the SCR, still I am not applying reverse breakdown voltage. Whatever the reverse voltage I am applied, that is less than the reverse breakdown voltage. With that assumption only, this concept I am explaining. That is, if the applied voltage is less than the reverse breakdown voltage in SCR, a small leakage current is passing through the SCR. This canal, the small canal indicates reverse leakage current. If the applied voltage is less than the reverse breakdown voltage, below the reverse breakdown voltage, then there exists a small leakage current in the SCR. That leakage current is called reverse leakage current. Okay, that is third observation. See the fourth one. Okay, we are applied only a small reverse voltage. Because of that reverse voltage, SCR acts as open switch and it carrying only leakage current. If you continuously increase the reverse voltage across the SCR, if this voltage is continuously increased, then what happens? If the reverse voltage across the SCR is continuously increased, and if that voltage across the SCR, if VAK greater than or equal to VRB0, if the applied voltage across the SCR is reaches to, you continuously increase this reverse voltage, whenever that reverse voltage is reaches to reverse breakdown voltage. We know that under reverse bias condition, J1 and J3 is open. Every junction is having its own withstanding capability. Now, whenever VAK greater than or equal to VRB0, J1 and J3 is breakdown. Suddenly J1 and J3 is breakdown and current sharply increases. Because of this high reverse current associated with the high reverse breakdown voltage, a large power loss is exist. And because of large power loss, there is a high temperature rise and SCR may be damaged. Hence, don't operate the SCR under reverse breakdown condition. If you operate the SCR under reverse breakdown condition, SCR may be damaged. That is, if VAK greater than or equal to VRB0, then J1 and J3 is breakdown. Then which breakdown this one? Which breakdown? It is avalanche breakdown. Why you are telling that it is avalanche breakdown? Then by applying the reverse breakdown voltage or reverse voltage, we are break down the junction. That's why it is treated as a avalanche breakdown. That means if VAK greater than or equal to VRB naught, J1 and J3 is avalanche breakdown. J1 and J3 is avalanche breakdown. And a sharp increase of current. And a sharp increase of current. Causes damage of the SCR. Hence, don't operate the SCR. Don't operate the SCR under which condition? Reverse breakdown condition. Don't operate the SCR under reverse breakdown condition. Then what the fifth observation? Every point is important for all competitive point of view. Clear? This is sharp increase of current causes the damage of the SCR. Hence, don't operate the SCR under reverse breakdown condition. Here I given two characteristics. Concentrate. Two characteristics I given. This is with load. This is without load. With load. That means we are operating the SCR some without load and we are applying some reverse voltage. In that case, the characteristics are straight line. A sharp increase. If the same SCR is operating in reverse breakdown condition, connecting with some load, consists of some load, then in that case, the characteristics are slightly bended towards the right side because of the load parameter. Okay. Without load, straight line characteristics we can get. But if any load is present and apply the reverse breakdown voltage across the SCR, in that case, the characteristics are slightly bended towards the right side. That's why I given the two characteristics that you concentrate. Okay. Then fifth observation. Under reverse blocking mode, tell me which junction blocks the high voltage? We know that under reverse blocking mode of operation, J2 is closed, J1 and J3 is open. J1 and J3 is open means what? For example, we are applying this 500 volts. But the voltage blocking capability of J2 is ideally 0. But practically it is very small voltage. Now tell me, in J1 and J3 only blocks this 500 volts. Now in the 500 volts, which junction blocks the high voltage? Yes, J1 blocks the high voltage. Under reverse blocking mode of operation, among all the junctions, J1 blocks the high voltage because we know that J3 is a junction between highly doped and less highly doped. J1 is the junction between less highly doped and less doped. That's why J1 is having less doping concentration. J3 is having high doping concentration. If the doping concentration is increases, what the blocking capability reduces. But it is having less doping now. That's why J1 blocks the high voltage. Next, J3. Next, J2. Understood? Therefore, in reverse blocking mode, among all the junctions, then J1 blocks high voltage. J1 blocks high voltage. J1 blocks high voltage. Sixth observation. Tell. Under reverse blocking mode of operation, the characteristics of SCR is similar to that of diode characteristics. You seen diode characteristics under reverse bias condition. These characteristics and diode characteristics are same. But under forward bias condition, SCR and diode characteristics are not same. In reverse bias condition only, the characteristics of SCR is same that of diode characteristics. That is, under reverse blocking mode, The characteristics of SCR, the characteristics of SCR is same that of diode characteristics, same that of diode characteristics in reverse bias, same that of diode characteristics in reverse bias. This is sixth observation. All these points concept I explained without connecting gate terminal. Now you tell me, under reverse bias condition, if the gate supply is given, what happens? Under reverse bias condition, if the gate supply is given, what happens? You will see. See, this is the seventh observation. This is seventh observation. Okay. Under reverse bias condition, if the gate supply is given, what happens? Seventh one. Yes. Okay. Now we know that J1 is open, J2 is closed, J3 is open. Now we are applying the reverse voltage. Okay. Then J2 is closed, J1 is open, J3 is open. Now we are connecting the gate supply with respect to cathode. Let this current is IC and this current is BC. That is, under reverse blocking mode of operation, if the gate supply is connected, under reverse blocking mode of operation, if the gate supply is connected, then where we are connecting the gate? J2 junction. J2 junction is already closed now. That means under reverse bias condition, by connecting the gate terminal, what we are doing? Already closed junction. J2 is already closed junction. Already in closed junction, again we are injecting the carriers. Extra carriers are injected because of the gate supply. But there is no effect of J1 and J3 now. Still J1 and J3 is open. But we are injecting the more number of carriers already closed junction, already in closed junction. That means due to this, number of charge carriers at J2 junction is increases, but J1, J3 is not affected. Once the J1, J3 is not affected means then SCR will not turn on. Then because of these charge carriers, extra charge carriers, the magnitude of leakage current is increases, but SCR will not turn on. Hence, don't give the triggering pulse. Under which condition? Reverse bias condition. If you give the triggering pulse under reverse bias condition, SCR will not trigger. But if you continuously increase the gate current, after some time, J2 will be saturated, then J2 will be damaged. That means in reverse blocking mode, if gate supply is connected, magnitude of leakage current is increases. Magnitude of leakage current is increases. Leakage current. Magnitude of leakage current is increases. Magnitude of leakage current is increases. Hence, don't give triggering pulse. Very important point. Hence, don't apply triggering pulse. Don't apply triggering pulse under reverse bias condition, under reverse blocking mode. If the gate current is continuously increased during reverse blocking mode, if the gate current is continuously increased, continuously increased, the gate current is continuously increased, then J2 will be damaged. J2 will be damaged. These are the observations under reverse blocking mode of operation. All these points are very important for any competitive point of view. The first point I discussed, under reverse blocking mode, which junctions are forward bias and which junctions are reverse bias. Yes. Second point I discussed, under reverse blocking mode, SCR acts as open switch and blocks the reverse voltage. Third point I given, there is no current from anode to cathode, but a small leakage current is exist, that is called reverse leakage current. Fourth point I discussed, if you continuously increase the reverse breakdown voltage, then J1 and J3 is breakdown, then a sharp increase of the current causes the damage of the SCR. Hence, don't operate the SCR under which condition? Reverse blocking mode. That is reverse breakdown condition. Under reverse blocking mode, among all the junctions, which junction blocks the high voltage? Then J1 blocks the high voltage because of less doping concentration. Understood? Then in reverse blocking mode, among all the junctions, another point I given, under reverse blocking mode, the characteristics of SCR is same that of which characteristics? Diode characteristics under reverse bias condition. Okay. Understood? Then under reverse blocking mode, if the gate supply is given, what happens? The magnitude of leakage current is increases. If you continuously increase the gate current, then J2 junction will be damaged. Hence, don't give the triggering pulse under what condition? Reverse bias condition. These are the observations under reverse blocking mode of operation. Okay. Now we'll see what is the forward blocking mode of operation of SCR. Then what is the observations from the forward blocking mode of operation. This I discussed up to now. All these 7 points up to this. Then this is under reverse blocking mode. Now we concentrate on forward blocking mode of operation.